All right. So, hello everyone. Good afternoon, good evening, good night, good morning, wherever you are in the world. So, hello everyone. Good afternoon, good evening, good night, and good morning, I'm hearing myself feeding back. Hold on. And I'm hearing myself. There. All right. So it's 5 o'clock. Today's student is CJ. We're gonna do some IB physics. Specifically, he requested to do waves, and I'm gonna let him in now. Okay, so I'm waiting. Let's just wait. Hmm. There. Hmm. All right, so while waiting for CG to connect, we're gonna do waves. We're gonna do basically units 4.1 and 4.2 in the IB syllabus. That's oscillations, wave behavior, wave properties. Okay, so traveling waves to be specific. Um, okay, in this under traveling waves, we have the two kinds, which is longitudinal and transverse waves. Then we will go through electromagnetic waves as well, just a brief introduction of that, and just some properties of those waves. Okay, for today's stream, we will stay in for about 50 to 60 minutes, and then I'll be signing off right immediately after that because I have to do something after that. Let's see the chat who's here while we're waiting. And Akira says, is that you, Akira, from class? Think so. Yo. Hmm. So, all right. So let's just start set. Let's just set up the. Excuse me. Let's set up the boards here. So 4.1 is all about oscillations and simple harmonic motion. Okay. Simple harmonic motion. Okay. Wait. Hold on. I'm changing pens after this. Okay, should use that pen. All right. Then 4.2 is about basically waves in general, specifically a traveling waves. Now, some of you who are watching, this may be either familiar or will be familiar to you soon because this is it's like these two bits. These are the introduction to more complex wave behavior. So if you'd like to listen in to kind of understand this, go ahead. You can stay. I wonder how many are on the streams. I'm gonna check. Gonna do a quick check on Facebook and YouTube right now, and might as well check Twitch. How many are watching here on Twitch? One person watching. I think I think Twitch counts your own view as a view, so it's probably me. Okay.
Hello?
All right. Hi, CJ. CJ's here.
Hi.
Hi.
Sorry.
No
Like,
problem. No problem. What
I was
happened
so
there?
good. Yeah.
Hold on. Let me get you on my. Let me get you here. Okay. So from I see you changed to Wi-Fi. All right. Yeah. Okay. No worries. Okay. So you asked for topics 4.1 and 4.2. That's basically the first two units for introductory to wave motion, right?
Mm-hmm.
Mm-hmm. All right. Uh, I have a quick question. Oh, by the way, the
Yes.
have I shared the Jamboard with you there? Yeah, I have. So the Jamboard link's been shared with you. Quick question first. What are you familiar with? We'll start from there. What are you familiar with?
Um, Superimposition.
Superimposition. Okay. What else?
Uh, Wavelength,
Wa-
frequency, like wavelength is lambda.
Wavelength, frequency. So probably the speed equation as well.
What's it called? There's like open end, close end,
Mm-hmm.
and like in like a loops.
Okay. So closed and open ends. Okay. So this is basically harmonics, right?
Yes,
And under
harmonics.
harmonics, this would be for standing waves. Okay. Well, anything else?
Hmm. Not right. Not that I can think of right now.
All right. So, all right, let's go to the very first one then. Okay. Are you familiar with this? Um, not really equation, but are you familiar with? Hold on, let me change board views. Okay. All right. Are you familiar with this? A is proportional to um negative x. Are you familiar with this?
No.
No. All right. Now, this you should be familiar with this because this is the basis for all things we do for waves. Okay?
Mm-hmm.
Because if you think about it, I'll get back to this later, but you're already familiar with waves, right? And can you define for me what a wave is?
Uh, a wave has a crest and a trough. I
Crest
don't
and
know
a
how
trough.
other how else to
Okay.
explain it.
Now, I'm gonna
Sorry.
say this much. This is partially correct. Okay. And this is one property of a wave. Okay. However, the best way to define a wave, okay, a wave by definition, this is the definition, okay, is a disturbance in a medium.
Mm-hmm.
Okay, it's a disturbance in the medium, where energy is transferred but not matter. Okay.
Mm-hmm.
All right. So where energy is transferred but not matter. Okay. Okay. What does this mean in particular? Okay. So if let's go back to our classic definition of a wave, our one of the classic examples of a wave. So for example, you're here, that's you, and this is me, right?
Yeah.
Okay. Then we're holding a rope, and then on the rope, basically you send a wave down the rope, right? So
Mm-hmm.
that rope is gonna move. Sorry, not the rope, but the wave is gonna move from you to me. And what happens? The rope,
It's gonna.
go ahead.
Oh, is it gonna flip and then return back to you?
That's one way. That's one thing that would happen, right? That's one thing that what would happen. Um, Another thing that you can think of here is that this wave, as it moves forward, it carries energy away from you and it brings it to me. Okay, so
Yeah.
energy moves that way to me, right? But the motion of the rope is only like oscillating. It's only going up and down. The rope itself doesn't really move anywhere. It stays where it is with the occasional moving up and down, right? So that's what it means to be a wave. You are transferring energy by making the energy move through the material, in this case the rope, by the wave. But the rope itself doesn't really go anywhere. Okay? So the
Mm.
rope does not go anywhere. Okay, so this is the key aspect of a wave. As long as the material itself doesn't move anywhere, but the energy of transfer happens, you have a wave. You see, of course, that's how you would define it, but of course, you know it when you see it, right?
Yeah.
Okay, so what does this have to do with this equation, though? Okay, because a wave, for most waves are oscillating. Okay, there are a few even the waves that you would not consider to be a wave, like single pulses, all waves have some sort of oscillation on them. Okay, okay, somebody's on the stream. Hey, Breden, whoever, Breden's,
Mm.
is that you?
But there's also and Akira and
Yeah,
Akira.
yeah, that Akira is like a grade 9 student, I think, one of my grade 9 students.
Oh.
Ah, all right. So anyway, so waves will always involve some sort of oscillation, which is
Mm-hmm.
another way of saying back and forth motion, right?
Mm-hmm.
Okay. So that means, because of this particular thing about waves, this means that we need to look at what oscillations are. Okay. So
Mm-hmm.
so basically we've defined what an oscillation is here, but the thing here is, let's kind of think about it this way. Okay, if you have an oscillation, what are the conditions?
Mm.
Okay.
Oh, the amplitude will be the same.
Mm-hmm.
Like
So
amplitude is consistent.
okay, amplitude's the same. Uh,
Frequency is the same.
Amplitude.
No?
I'll just say amplitude. Then you have frequency. Um, what else do we know? Well, we're just gonna be a wavelength here, right?
Mm-hmm.
Okay. Now these would be actually the result of the conditions. It's not the actual conditions. Okay. So these are the result.
Mm.
Okay. Now, let's kind of look at this now. What are the actual conditions? Now, there are two ways. The easiest way for you to think about oscillation is this. If you have a mass, this can be any kind of mass, right? But the simplest possible case is you have a mass, and then this mass is connected to a spring, right?
Mm-hmm.
Now, let's say that this mass is moved this way so that it's now here, right? So when you do that, what happens to the spring?
Um, isn't there like gonna be like a stronger force to pull the mass back?
Yeah, but where's that stronger force coming from?
The 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 node.
Okay, okay. Actually, no. The node is just some other thing that goes into standing waves, which is basically a little one step beyond what we're trying to do. Okay. So what happens here is, if the spring is originally this way, you stretch the spring, right?
Mm-hmm.
So stretch the spring. Okay, so because the spring is now stretched, that means that spring is exerting a force going this way. Force, right? Now, one more thing about this is that if this were the original position of the block, then that means this is your displacement x, right? So
Mhm.
going back to the force before we finalize, before we actually go to the thing, okay? This force, this is basically equal to ma, with this having a mass m, right? So in other words, the acceleration is also going that way, right? Okay.
Yeah.
So what is happening here between x and a? X and
Um.
a are oppositely directed, right?
Yeah. As
Okay. Now, no matter what you do, no matter what you do, whatever happens, the acceleration is always, the force is always going to be the other way of x. So for example, you have your original spring looking like this, and then you compress it, the spring's going to look compressed like that, right? And that's your mass here,
Mhm.
and now your mass is here, right? So our x is going this way, but the force is going to be pushed out,
Mhm.
right? So in this case, same thing, x and a are still oppositely directed. So in both cases, we can now say that a is definitely proportional to something about x, but since it's opposite, it's going to be negative, right? Okay. Now,
Right.
one thing about this is this one condition is the condition for simple harmonic motion. And simple harmonic motion is the motion that makes all kinds of oscillations and therefore all kinds of waves possible. Simple harmonic motion. Okay. Oops, didn't. Okay. So again, this particular equation is where simple harmonic motion comes in. So whenever you see this term, simple harmonic motion, it's just basically a back and forth motion wherein the acceleration and the displacement. So let's write that up. Write that in. So acceleration and displacement are oppositely directed and directly proportional. As x increases, a increases, and the other way around. Okay.
Mhm.
All right. So again, this is the key condition, and I've actually seen a couple of problems in several papers, not just IB, but in several other papers, basically asking this. So what if your acceleration, so let's kind of look at this. So let's take a look at a few graphs. Okay,
Would you say x is the distance or the displacement?
displacement.
Okay.
Okay, let's say that this is your displacement and this is your acceleration, right?
Mhm.
Okay, so what kind of graph would that look like?
Um. As x increases,
As x
the
increases,
acceleration doesn't it increase?
it increases but negatively, right?
Yeah.
So increases but negatively would be somewhere as x increases but negatively would be here, right? So something like that, right? And of course, if your x is negative, then your a is positive. So the graph, this is how the graph of simple harmonic oscillator looks like. Okay, and all right, you see that we have a limit.
Yeah.
Okay, what do you think this is? This is the maximum displacement. Now I think you remember what this is defined as.
Uh,
Okay,
amplitude.
this is exactly the amplitude. Okay, so
Okay.
whenever you have a wave, let's kind of go into like a wave first before we go into that. So what happens here is this is your max displacement A, right? So this
Mm-hmm.
to this would be A, and here would be negative A, which would correspond to this point. Okay, so whenever you see a graph of acceleration versus distance or acceleration versus displacement, you would always expect a straight line graph, and it's going to have boundaries like this. It's not going to go on forever.
Mm-hmm.
Okay, so that's the first part. Uh, what's another possible graph here? I think for now that's it. Okay. However, let's kind of look into this now. Okay. So that's your maximum amplitude. So A is max, right? So that means
Mm-hmm.
X here is also max, but negative. This is a positive max, right? At this point, what do we have? We have a negative maximum for A, but a positive maximum for X. Okay, positive here. Okay, so in other words, if you're really gonna look, another good example for a simple harmonic oscillator is a pendulum. It's not a perfect example, but it's a really common one. Okay, so let's take a look at the pendulum. So in case that's your pendulum, and I'm gonna make it swing a very small angle. So it's just gonna look like that, right?
Mm-hmm.
Okay, and it's gonna swing either way like that, right? So where's our amplitude? This would be the amplitude, right? From here to here is also the amplitude. So where do you have minimum, or rather maximum acceleration to the left? Which point? Let's call 2 points A, and let's not use A. Let's use
Um,
PQR. Yeah. So let's just P. This is point P. This is point Q, and this is point R. Where do you find maximum acceleration to the left?
to the left.
Yep. PQ or
I
R?
thought um 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 I thought Q.
No, no, it's
Oh,
not Q. I'll tell you why later in terms of the common sense and then in terms of the equation.
is Q the highest velocity point?
Correct.
Like,
Q
okay,
is the highest velocity point, yeah?
yes.
Velocity max.
Then if it's to the left, it's R.
Yes, correct. R is correct, yeah? So max acceleration to the right is what?
P.
Okay, correct. Equals P. Okay. Now, if we're gonna put this into a graph, not a graph, a table, and we're just gonna compare um, X, V, and A to the different points P, Q, and R, right? X would be a positive maximum. No, in P, this is a negative maximum, right? Negative
Mm-hmm.
max. V here would be at P. What's the velocity at P? Let's zoom in a bit. Okay, at P, what's the velocity?
0.
Zero, exactly, because you know that in reality what happens, that's where it stops for a while before turning back, right? Okay,
Mm-hmm.
and A here would be a positive max. Okay, all right. How about Q? What's the velocity? What's the position of X at Q?
Mm,
Because Q is the equilibrium position, it's our
0.
initial position, so X is
Q is 0.
0. At Q, V is, we don't know what exactly the value is, but we know it's going to be a
Max
maximum. Okay, and acceleration is going to be also
0.
0. Then for R, what do we have?
Same as no, it's positive max.
Positive max, correct. This is 0, and then this is a negative
Is it?
max.
Oh, it's negative x.
Mhm.
Oh, okay.
Why negative max? Because it's pointing to the left.
The direction.
Yeah, direction. So basically, these positives and negatives, these are just directions.
Right.
Okay. So same thing with that. These positives and negatives are just directions. So don't, if somebody asks you what the minimum speed is, so basically it's better to say that this is not really displacement, sorry, not really velocity. This is better mentioned as speed. Okay.
Mm-hmm.
All right. However, for displacement and acceleration, we have to keep um the positive and negative. Now, anyway, for point Q, let's just do that quickly. We can do a positive and negative there simply because at Q, you could be going from P to Q to R, or you could be going from R to Q to P. So it depends on the context here. Okay.
Mm-hmm.
All right. So, okay. Now, finally, for simple harmonic motion, let's move into that to this equation. So far, I only gave you the proportionality that A is proportional to negative x, right? There is a defining equation for simple harmonic motion, not a relationship, but an actual equation. Okay, acceleration is equal to negative omega squared x. This omega is the angular frequency. Now, this angular frequency at this point does not necessarily mean there's something is rotating. It just is defined as 2 pi times the frequency. So omega is equal to 2 pi times the frequency. Okay. So
Mm-hmm.
for any simple harmonic motion, the equation is this. For any simple harmonic motion um, problem. Okay. So again, for any simple harmonic problem, simple harmonic motion problem, that's the defining equation. Um, According to the book, we don't need to go too deep into this, but I think it's a good idea to just
Wait.
explore this. Okay,
Sorry.
go ahead.
What's the W again?
Angular frequency. So let me redo
Mm.
that. Let me highlight that. So this
Yeah, I never
omega
really understood
is
this
this.
in class.
Okay,
Yeah.
I think you've studied this before, but it doesn't make sense, right? Where did the word frequency come from all of a sudden, right?
Yeah.
Okay.
And
Um,
angular.
okay. But I think we have established why we have the negative, then proportional to then x, right?
Mm-hmm.
Okay, we need to establish where that where that omega squared or that w like thingy comes
Mm-hmm.
from, right? Uh, let's go back to circular motion. This has something to do with circular motion, but don't think of this as the object making the wave undergoing circular motion. Okay, but know that this is related somewhat to circular motion. Okay, I'll try to explain this very briefly, but as you know, the idea. Okay, the idea here is imagine you have a coil of something. So you have this coil, right? So this is a coil with a circular cross section. Okay, and then if you change your point of view, change POV, you can actually so that the coil is horizontal. It's gonna look something like that. Okay, in case you're not you still cannot visualize that, let me look for something I can turn to a coil real easily. Okay, then it's gonna work. Hold on, give me a few moments. I'm just gonna get a wire. All right, here we go. So okay, you can see the wire, right? Oh, let me go back to normal board. Yeah, normal screen. Okay, so you see this
Mm-hmm.
straight wire, right? Okay, I'm gonna
Yes.
make this straight wire into a coil like this.
Mm-hmm.
Okay, It's not perfect, but I think it will do at least for our purposes. Okay. So you can I hope you can see that this is definitely a coil, right?
Yeah.
Okay. Now, if you look at it this way, or you can look at it this way, or you can look at it at any angle, it looks like a coil, right? But if you align your coil in a very particular manner, like this, it kind of looks like a wave, a frozen wave, right?
Yeah.
How do you make that wave rotate? No, not
Um,
how do you make the wave move? And what we
you
normally do is we do this, right?
increase the frequency.
Okay. Now, you can do that. And when you increase the frequency, basically that what you're saying is I'm doing this faster, right?
Yeah.
All right. But another way to think about it, somebody sneaking in. All right. Okay. So anyway, here's the idea. All right.
Hmm.
Instead of making the wire itself stretched out and then make the wave, you can think of this as I rotate the whole thing. When I rotate it, it looks like the wave's moving forward, doesn't it?
Hmm.
Okay, so that's the idea of where the circular motion comes in. This particular rotation of that coil is similar to what you would get if you make a wave do this. Okay, so that rotation of the coil provides you with the uh so if you go back to the board, that rotation of the coil provides you with that with this angular frequency. Okay, excuse me, hold on. So anyway, the idea here is that in circular motion, if you recall, there's this quantity called the angular uh, velocity or the angular speed, right?
Yeah.
Okay. This is also given the letter omega. These two are actually the same thing, same idea. But again, if you don't see the link between the coil rotating and the coil showing that wave-like motion, then it's gonna be really difficult to see where that omega comes from. Okay. All right. But anyway, just to make it easier, because you're taking SL, all you have to know for SL at least is that the angular frequency is defined by this. So if you know the frequency of the wave, you can find, or not the wave, but the frequency of the oscillation, you can find its own angular frequency. And if you
Hmm.
find the angular frequency, you can find the acceleration if you know its displacement.
Yeah. Wait,
Okay?
is the angular velocity like the rotation movement?
Yeah.
Okay.
Okay. So the faster you rotate that, the faster the wave seems to progress, right?
Hmm.
Okay. I'm gonna either try to shoot a video of that or look or make a simulation out of it. I think a
You should
video is
make a
easier.
simulation with a slinky. You know, when you drop it, it goes
Yeah.
like,
Actually, I've done it before, but I never took a video of it. I literally have not a slinky, but a big spring from a car or a
yeah.
motorcycle, and then you just
Oh,
rotate that. It's much easier seen. I'll try to make a
yeah.
video of that once I get a hold of a big spring or a big enough coil at least.
Okay.
All right. Anyway, uh, going back. So for SL, again, all you have to remember is this particular equation for angular frequency. All right. Okay.
Yeah.
All right. So that's 4.1 in a nutshell. Okay. 4.2 in a nutshell, you already know. So we're not, I think if I look into the book, I'm going to look into the book real quick. Where's the book? Okay.
Also,
4.2.
for the momentum test,
Uh-huh.
I got a 7,
A grade of 7.
like 8 out of 10,
8 out. Oh, awesome.
surprisingly,
Yeah.
because like, yeah, what you were telling me about was like on the test as well.
Uh-huh. Which one specifically?
Something about the the masses part where it's like,
Mm-hmm.
what's the moment? Like, what's the change in momentum
Mm-hmm.
of like a mass that's like collided?
Right. So again, the idea there is if it's just a single mass, go ahead calculate that. But if it's for the whole system, it's always going to be
Yeah,
0. Yeah.
yeah.
Great. Great. It's good to hear. Um. Okay. 4.2. It's mostly the finer details. I think that you need to go for 4.2. There's still one thing I need you to go through for 4.1, but I guess that one's easy. Okay. In 4.1, we also have the energy of the oscillation. Energy of oscillation, right?
Mm-hmm.
Oscillation. Okay. Now, of course, due to conservation of energy, okay, what we're going to do here is we're going to look at the single particle on our oscillating, on our wave, right? So this particle here is going to go up and down, then into the equilibrium position, then into here, right? So let's kind of put something into here. The Okay, or better yet, let's not do it like that. Let's not do the graph. I think we better do it with a real object, even if I just draw it. Okay, let's take a look at the pendulum again. Okay, so again, we're going to draw our pendulum with our three positions P, Q, and R, right? Hold on. Later, later. Okay, so anyway, okay, for those in the stream, that's my kid. Yeah, okay, and she wants to tell her a fun fact. Quick one,
Really?
just one.
Milk can be good for plants, and I don't know why.
Well, okay, we'll find out later why that's the case. Yeah. All right. So anyway,
Milk is good for plants.
milk is good for plants. I don't know where she got
Oh,
that.
I remember doing that in third grade
That's cool.
Uh huh.
where I put milk in plants. I remember it in
Uh,
third grade.
what happened? I'm curious.
Happened with
I don't
what?
remember. I just remember my friend telling me a joke that he said he drank it and it tasted good, like the
What
whole
happened
milk in the
after
soil.
Okay. All right. So
Yeah.
anyway, let's go back here. Okay. So we know that here. Let's put the idea here that x is maximum but negative. A is positive maximum, right? And V
Mm-hmm.
is 0. Here, x is positive maximum. Sorry, x is 0, right?
Mm-hmm.
X is 0, A is 0, and V is maximum, right? Whether it's positive or negative. And at R, we again do that. X is positive maximum, A is negative maximum, and V is 0, right? Okay. So where do we have, so think about it this way. In this particular case, where do you have maximum potential energy?
Is it PNR?
P and R, right? Exactly.
Yeah.
So, so the maximum KE, maximum kinetic energy, is gonna be here at Q. Okay,
Mm-hmm.
so that makes sense because due to conservation of energy, if you don't push that pendulum regularly, it's just gonna, and then let's say it's ideal conditions, then it's just gonna swing back and forth between P and R forever, right?
Mm-hmm.
So if you're gonna graph that, this is the energy, right? And this is displacement. How will that look like? Let's take a look at kinetic energy first. So let's use green for kinetic energy. Okay, kinetic energy would be maximum where? At x equals 0, right?
Yeah.
And then it's gonna slowly decrease to 0 either way, either side, or something like that, right? So Ke. How about potential energy? What happens here? So let's say
Um,
Pe. Where do we have maximum Pe?
PNR.
At P and R. In other words, the amplitude points again, right?
Yeah.
And what happens at Q?
It's like no potential energy.
No potential energy, 0, right? So it's gonna look
I
some.
I only know potential energy and kinetic energy because like I look at it like potential energy is like when it's at a high place but then when it's
Uh-huh.
at the ground, it's like max kinetic.
Yeah. All right, that's actually a good way to look at it. But of course, this particular graph will apply to all kinds of oscillators, not just a pendulum and gravity. It can be springs on
Yeah.
a mass on a spring. It could be the particles of water in a wave. As long as it does this, as long as it does simple harmonic motion, this is how the energy graph looks like. And of course, total energy would be what? Let's use black for total. So this is PE, right? So total energy would be, does it change?
Mm. Total energy?
Again, let's assume ideal conditions.
No.
No, it doesn't. So the graph would look like this for total energy.
Hmm.
Okay. So for a simple harmonic oscillator, this will always be how the graph looks like. Okay. Now we have other graphs, but I think the best way for us to consider the other graphs is we actually do problems, and then when we encounter them, we explain them there. Okay. All right.
That's good.
So, all right, is this part clear? The energy of oscillations.
Yeah.
All right. So, uh, let's actually do some problems with the first one. Uh, let me just check if you need the actual formula. Actually, in SL, you don't need the actual formula for. Ah, yeah, you do. You do. So,
Oh.
okay. So I'm gonna give you. Well, at least you know. Let's just say it like this. At least for SL, all you need to know is that the acceleration is proportional to negative x squared, negative x, right? Okay.
Mhm.
I'm just gonna tell you now that for HL they need the equation negative omega squared x. So for you, this will suffice. Okay.
Mm.
All right. Now, what does this mean though? If you're given a certain condition, that means, for example, if the acceleration is equal to negative 3x, right? What does this mean? In SL, this means automatic simple harmonic motion. That's all you have to say. It's simple harmonic motion. In HL, just so we know what the difference would be in the answer, you would be expected to say that omega squared is equal to 3, then omega equals square root of 3, then solve for frequency from whatever. Okay? So for you, all you have to do is identify from the equation whether it's simple harmonic motion or not.
Okay.
Okay? Got that?
Yes.
All right, great. So, is there anything else I missed? I think that's it for 4.1. Okay, there's one more thing. I'm just looking at the book. I think there's one more thing. Phase difference. Oh, you need to understand phase difference so you can understand 4.4. Okay, phase difference. Okay, now the easiest way to do this is to just think of three waves. Okay, all right, I'm gonna copy an image from the book we're using. The book we're using is the Physics for the IB Diploma by Mr. Chokos, and hopefully he doesn't mind me using this real quick. Okay. All right. So here's the idea. We have these three waves: the red, the green, and the red, the blue, and the purple wave. Right? Okay. We
Yes.
are gonna use which wave? Let's use the blue wave as our reference point. Okay. So blue is the reference point. Okay. Yeah. Okay. So for blue is a reference point. Okay, I think we better go through more detail here next time. But for now, I'll just gonna briefly discuss this. Okay, blue is the reference wave. Okay, now red. I'm going to say this now. Red is 1/8 of a wave behind, right? I'll explain later how I got that 1/8. Okay. Then that means for red, the phase difference between red and blue is 360 degrees divided by 8. Okay? And because red is behind, we're gonna put negative in there. So what's that gonna be? 360 by 8. 360 divided by 8 is gonna be 45, negative 45 degrees um phase difference. Okay. Similarly, purple would be a positive 45-degree phase difference with the blue because it's 1/8 of a wave ahead. I guess we'll go through next week or next lesson on how we know it's 1/8 of a wave or 1/4 of a wave or full wave or whatever. Okay.
Mhm.
All right. So we'll end phase difference here. I think we better do some quick examples here. Okay. Uh, okay. Let me check something. Uh, okay. Can you tell me whether this is okay, I think I'll just use Mr. Chocos's book again. I'm just gonna do some simple problems right here first. Okay, so let's answer numbers 1, 2, and 3. I want you to answer them first, and then I'll tell you whether they're right or wrong. If they're wrong, I will um, give suggestions how to improve the answer. Okay. All right. Number
Mhm.
1. What's your answer for oscillation? What does it mean?
Oscillation,
Mm-hmm.
when uh a wave that is sent and reflected back the
Mm-hmm.
same,
No.
like
No.
oh
Unfortunately, no. Okay. Again, an oscillation is simply a back and forth motion, a
oh
repeating back and forth motion. I think I'll type that in. See, it's gonna be clearer. Okay. So an oscillation is a repeating back and forth motion. Okay. How about simple harmonic motion?
everything. Wait, simple harmonic motion, isn't that like, I thought everything it stays the same.
Not quite.
uh does that have anything to do with harmonics?
No, it has something. Well, kinda, but it's gonna be better done if it has something to do with oscillations. Simple harmonic motion is basically oscillation, but it's got a special condition.
um
Again,
I
what
don't know.
give you a clue? I'll go back to something right here.
Oh, uh hmm hmm acceleration indirectly proportional to the displacement.
Okay, so what does this?
um
You don't say indirectly in this case. You say um.
acceleration is the opposite direction of the displacement.
Okay, so you have to say that this is oscillation, where acceleration is the is direct direct oppositely directed directed from the acceleration and from the displacement and what is directly proportional to it. Okay, so I guess I can give you partial mark for B on that one. So again, the key idea for oscillation is that it's repeated back and forth motion. It doesn't have to be um, okay. A good example for an oscillation that's not as simple harmonic oscillation or not simple harmonic motion is when you're bouncing a ball against the wall. You keep doing that.
Mhm.
Okay, you keep throwing the ball into the wall. Yeah, it's repeating, it's oscillating, but it's not simple harmonic oscillation. Okay, so I'm giving you a clue for number two. So you have a ball bouncing back and forth along a horizontal floor, bouncing off two vertical walls. So there's no person there. So basically, you just throw it into the wall, and then the so basically the idea here is this is the wall, and this is your ball. Your ball is going that way and that way. Is this is this an oscillation or not? And if yes, is this simple harmonic or not?
Oscillation, yes, but you
Mhm.
said no for simple harmonic
Why is it not simple harmonic?
because doesn't it like lose speed? No,
No, at this point we're still assuming it's ideal.
ideal. It's
So no loss in energy, nothing. It's just gonna bounce between the two walls forever.
mm, why is it not oscillations?
Okay. All right. So again, you're in
Is
the
it like
right path.
related to
Acceleration
acceleration?
is proportional to x, negative x, right?
Yeah,
Okay.
the
This is
acceleration is the direction of the displacement.
mhm. It depends on the displacement, correct? But in this case, it's I already told you it's not, right? So this means that this condition is not met. Now think about it. Why is
Yeah,
that condition not met? I'll give you a
because
clue. I'll give you a clue.
yeah,
Okay. Remember, are there any what are the forces acting on the ball here? It only happens where? Only happens there. Let's change color to make it more easily seen. Only happens here, and it only happens right there. Do you have any forces on the ball anywhere else? Again, let's assume no gravity as well.
do we have any what?
Let's assume there is no gravity.
Mm-hmm.
Okay. So what happens? Does the ball actually experience a force everywhere it goes?
Yes.
No, it doesn't.
No, only at the walls.
Only at the walls. So force only on the walls, right?
Yeah.
So in other words, what happens? A only at x equals amplitude, right?
Mm-hmm.
So elsewhere, a equals 0. So this portion here, this kind of makes it simple harmonic motion, right? Could be simple harmonic motion or simple harmonic oscillation. But here, elsewhere, a equals 0 makes it not simple harmonic motion because it's no longer proportional to x. If your object is here, that still has a value x, but the a is equal to 0, not proportional, right? Same thing here. This has a value x, but your a here is equal to 0, also not proportional. All right? All right, let's do 3. Is this oscillation? And if so, is this simple harmonic? This time, for 3, you have a ball hitting the floor and bouncing up, then back and up, and so on. Okay? So is this simple harmonic motion? First of all, is it an oscillation? And second, is
No.
it a simple harmonic oscillation?
Um. I mean, is it oscillation? But
Again,
if it's
oscillation
not an
is
oscillation,
simply, let's go back here. What's oscillation again?
it repeated back and forth motion.
Is it a repeated back and forth motion?
Yes.
So, is this an oscillation or not?
Yes.
Yes, it is. So number 3 is oscillation, check, right?
Mm-hmm.
How about simple harmonic motion?
Mm, no. Wait. I feel like the
No,
acceleration would be the same.
the answer would be the same, but would the reason be the same? This is
I feel
actually,
like it'd
you're
be the
actually
same
correct.
if
This is not simple harmonic motion. You're correct. But let's see the reason why. Let's again
Mhm.
look at the acceleration. And where's the equilibrium position here? Do you have an equilibrium position here?
No.
Not,
Oh, I don't think so.
no, right? So
No.
in this case, let's even assume an equilibrium position. Let's assume this is equilibrium, right? Assume equilibrium, right? So what's the
Yes.
acceleration on this side? On this bit? The acceleration is equal to g, right? What's the acceleration above that line?
Um.
Above the line.
Oh, it's still 9.81, isn't it?
Exactly. Still 9.81, still g, right? And then here
Yeah.
we have a, at the floor, the acceleration is not equal to g, but also not equal to 0, right?
Hmm.
So what's our problem here? Go back to simple harmonic oscillation equation. Does your acceleration change with position or not?
No.
Generally speaking, no, right?
Yeah.
So A is not proportional to negative x, not SHM. There.
Hmm.
Got, okay? Is that clear now?
That's clear.
All right. The rest of this, it's basically using the equations and the graphs. We can do that next time and then move on to 4.2 afterwards. Okay?
Okay.
All right. Okay, so we can end it here, CJ. I'll see you next time.
Thank you so
All
much.
right. Okay. All right. Where's the window? Where is our window? Oh, here it is. Okay. So okay, I'll see you next time, CJ. Bye bye now. Have a good day.
See you too.
All right. Okay, CJ is gone. CJ is still on the stream, I think. Let me just get out of the classroom. All right. So, uh, all right. So yeah, waves. A lot of the time, yeah, we kind of know what waves are, but remember in physics, it's not enough for us to say that we know what it is. We have to actually define stuff. So that's why we need to define simple harmonic oscillation or simple harmonic motion first before actually going to waves. Because once we do those definitions and stuff, that makes it easier to define things and easier to describe things more mathematically. Okay, so in this case, the mathematics is simple harmonic oscillation, acceleration is proportional to x squared. So again, let's do a quick recap on that. So if you have your object here, and let's say that this is x equals 0, your equilibrium position, that means that there is this thing, and then it moves this way, and then let's say that that's displacement x, which is negative. There should be a force going the opposite way to make it go back to the uh let's go back to the board. So again, so here's the object, its original position, then it moves this way. In this case, our x is negative to the left. Then that means there must be a force directed in the opposite direction to put it back to its original position. Another physics term for this is there must be this restoring force. So you can define this. Now, it's called a restoring force because it will restore your object to the equilibrium position. Okay, so similarly, we go the other way. If this is your x, which is positive, then there must be a force going that way to restore it as well. Okay, so in both of these cases, the forces means the object will accelerate, Okay, so there's an A. Okay, so if force, or let's say it in another way. So the thing about force and acceleration from Newton's second law, F equals ma, this now means that wherever F is directed, A is directed in the same way. So F and A are directed in the same direction, are in the same direction. Okay, and with that, we'll end it here. So before that, so with that being said, so this means that the acceleration is always opposite of x. So we have negative x, and the force gets bigger the farther it is, just like with the spring. So it's going to be proportional like that. And again, this is the condition for simple harmonic motion. Once we have this condition, we can do a lot of math with it, and therefore a lot of physics with it. Okay, so we'll end it here. So let's go now to this. So again, I want to remind everyone, if you can, subscribe to the YouTube channel or Facebook page. You can follow us on Twitch for live videos. Okay. Also, Instagram and TikTok are now live, so we can actually interact there if you need anything. Okay. Now, at this point, remember, I'm just streaming my lessons with my online tuition students or online tutoring students. So if you'd like tutoring and you'd like to be streamed on like this, and you'd like your own tutoring, feel free to contact me later on. Okay. Otherwise, um, I can just put this stuff online for you to learn on your own, but I will not be able to answer your questions. Okay, so again, online tutoring is ready for people who are already subscribed to the tutoring service. Later on, anyone who wants tutoring, I will give I'll probably give a link on how to do it, but let's see later on. Right now, I'm very busy, so for now, I'm keeping just a couple of students. Later on, we'll see. Yeah. Right. Again, so don't forget to like and subscribe to all of these social media accounts or social media channels. And that's it. Thank you, freaks. I will see you again next time.